Okay, hey, welcome back. This is the last section in Chapter 9, and finally we'll be able to produce, we'll have a programmable way of producing representations of functions with power series. Okay, in particular, it all just comes down to what you learned about the Taylor-Maclaurin polynomials. So you'll see in section this Theorem 9.22, which basically says that if f is represented by a power series, then it has to have basically the same form as its coefficients have the same form as the Taylor-Maclaurin polynomials. Okay, so that's basically what it's saying there. The proof is pretty simple. You just presume that there is some sort of power series representation in some interval. So it converges in some interval, and the radius convergence is big R. In that interval, then we could take derivatives, and so here on the book here over here, you're seeing that power series representation. Then they're doing all the derivatives, and then they're taking the actual function and evaluating at all the centers. And then if you equate the function and its derivatives evaluated at those places to the power series evaluated at those places, you end up with the same formula that you got for the Taylor and Maclaurin polynomials. Okay. So then they give you the definition of the Taylor and Maclaurin series, which is basically just the Taylor and Maclaurin polynomials taken to the infinity, right? So the definition then, the power series representation for f, and it's just a representation, so it may or may not actually equal the function. And they show you that here if you're wondering what they're talking about in 9.25, this figure. Basically, they formed this approximation to this piecewise function using the Maclaurin series. The problem is, if you do that, you basically get an approximation for sine x everywhere. So it would have all kinds of humps, just like the regular sine x does. But the actual function is not the normal sine function, right? At negative pi over 2, it's just a horizontal line. At pi over 2, it's another horizontal line. The problem is that you create these functions centered at certain places. So if you create it centered at 0, you would never see these outer portions in your derivatives. So you would end up with a false representations, which is why we say that these things are representations of the functions and not actually technically equal to the function. And later we'll see they will be equal if certain criteria hold. So we'll say then from theorem, I guess it was 9.21, if f is represented by a power series for all x in an open interval I, containing the center C, then it must have the form of this power series, nth derivative evaluated at c all over n factorial from n equals 0 to infinity times x minus c to the n. And of course that equals f of c plus f prime of c times x minus c plus f double prime of c all over 2 factorial times x minus c squared plus dot 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 plus f nth derivative evaluated at c all over n factorial times x minus c to the n plus dot dot dot. It goes on forever. Okay. If c is equal to 0, it's a Maclaurin series, right? So this is, this form is the Taylor series representation And then if C is equal to 0, it's the Maclaurin series representation. Okay, great. So building these things is pretty simple. You just follow along with what you've done before. It may be a little more difficult with regards to formulating these summation notation formulas. So let's take a look at the first one they give us, example 1. They want the power series representation for f of x equals sine of x about c equals 0. In other words, they want a Maclaurin series for that function. Okay, so in order to pull this off, we basically need to find these things. And then you're basically just filling in the boxes, right? So you need these guys. Oops, now I want it in red. Okay, so you need to figure those dudes out. Right, so I got f of x is sine x. And what you do is just kind of iterate a bunch of derivatives until you can see the pattern. So you're not going to have to go crazy. Probably just with trig functions, you could go up to the 5th derivative is usually enough, and then on and on. What we're interested in then is, these guys evaluated at 0 for our pattern. Because eventually we want this formula for the nth derivative to put into our summation notation, right? Okay, so sine, then cosine, then negative sine, then negative cosine, then back to sine, right? And then it just repeats. So over here, sine of 0 is 0, cosine of 0 is 1. And so maybe it's not clear what the nth term formula should be, but something that is clear, I think, is the n plus first formula. So let me just keep it as fn. I'm not going to be able to get that formula right because it's kind of weird, right? 0, 1, 0. But if I look at the maybe I can kind of back engineer it if I look at the representation for it. So again, what I need is to kind of just fill in these boxes. Usually on my test, I'm happy if you can just give me the polynomial. I don't necessarily need you to give me the summation notation, but I think for the homework you're going to need the summation notation anyway, so you might as well, yeah. Alright, so I'm going to go 0, 1, 0, negative 1, 0, 1, etc. Rewriting it, make it look pretty. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then I can kind of see the pattern. X to the 7th over 7 factorial plus x to the 9th over 9 factorial minus so on. So in summation notation, I'm going to start at 0, I think, to infinity. And then I'm looking for a formula that creates this, right? So what do you have? You have some x, there's a negative 1 oscillating, so negative 1 to some power, then x to some power, all over some sort of factorial, right? Okay, so for the negative 1, I see that the even guys, the first, n equals 0, I need it to be positive. When n is 1, I need it to be negative. When n is 2, I need it to be positive. So if I just put an n there, that will work, right? Because when n is 0, that will be positive. When n is 1, that will be negative. When n is 2, that will be positive. Okay. Now I need a formula that generates the exponents and then the factorial. So if you look at the exponents, it's really a sequence, an arithmetic sequence, 1, 3, 5, 7, 9. So I need a formula in terms of n that produces that. You could literally use the arithmetic formula to figure that out. A sub n equals a sub 0 plus, what is it, n minus, or it's just n times d, I believe. Okay, so n times d. So in this case, it'll be 1 plus the difference is 2. So you have 1 plus 2n. And then make sure it works. You know, when you plug in 0, you get 1. When you plug in 1, you get 3. So this will be 2n plus 1 all over 2n plus 1 factorial. Honestly, when I was in your shoes, I would just guess the formulas and kind of get them right. Okay, but anyways, that will be your series. I don't know if they want the interval of convergence. No. And determine the interval of convergence. So I guess you would have to, do the ratio test. R is the limit of the absolute value. You can disregard the -1, so you got 2 times n plus 1 all over 2 times n plus 1 factorial times 2n plus 1 factorial all over x to the 2n plus 1. Gonna need a little room there. So that will equal the limit as n goes to infinity of x to the 2n plus 3. So that's going to be 2n plus 2 plus 1 is 2n plus 3 over 2n plus 3 factorial times 2n plus 1 factorial all over x to the 2n plus 1. That will be the limit as of the absolute value of x squared over 1 times 2n plus 1 factorial. That's 2n plus 1 times 2n plus 1 minus 1, which is 2n, times 2n minus 1 times 2n minus 2, blah, 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 all the way to 3 times 2 times 1, all over 2n plus 3 times 2n plus 2 times 2n plus 1. You're just looking for where the top and the bottom kind of match. Right, so you get this 2n plus 1 stuff kind of canceling out, and of course that will just be then the absolute value of x squared times the limit of 1 all over 2n plus 3 times 2n plus 1, or 2n plus 2 rather, which will be 0. In other words, r is equal to 0, which of course is less than 1, so that means its interval of convergence is going to go from negative infinity to infinity. Okay, so it converges everywhere. Right, so again, then in 9.25 there's a warning. These things are representations for the functions. They may not necessarily converge to the function, and it's because of the way we're building these things. You see, if you were looking at the derivative of the function, this piecewise function over here on the right in figure 9.25, that thing, if you build the Maclaurin series for it, you're evaluating that function at 0. So the only piece that you're using is that sign of x piece in the middle, and so you're kind of disregarding the pieces on the ends, and so your Maclaurin series won't take into consideration that part of it, and your Maclaurin series won't work. So then you come to this issue, well, when will it work? When will this thing actually equal the function that you're representing? And that's theorem 9.23, and it'll go back to that remainder formula that we saw earlier when we were working with the polynomials and doing approximations. Okay, so let's see if I want to make that a new section. Sure, so we'll make this section 2, convergence of the Taylor series. So basically we have theorem 9.23, and it says if that r sub n formula, the limit as n goes to infinity of this r sub n thing equals 0 for all x in I, then the Taylor series representation for the function f converges and equals f of x. Okay, So this last example, though we didn't show it, it turns out it does actually converge to sine of x for all x, and we may have to show that here in the book. Yeah. Okay, so they're going to force you to show that. Anyways, just a reminder of what the heck that r sub n of x thing was. Usually when we're working with it, we try to bound it. So reminded. So this r sub n of x thing, when we worked with it, we bounded it above by the max of the n plus first derivative on this interval from x to c, divided by n plus 1 factorial, and it was an absolute value of that, times x minus c raised to the n plus first power. It's that junk that you're going to have to be working with. Okay, so let's look at example 2, and basically we're trying to show that sine of x is equal to its Maclaurin series. So we're working with f of x equals sine of x. If you consider then what we need, well, n we kind of don't know in this thing. The c value, it's Maclaurin, so c is going to be 0, and this max value is going to end up being 1. So the max of the n plus first derivative of f on the number line basically is what we'll deal with. This portion of it is kind of, you'll just, the n plus first derivative is going to be one of 4 things, right? It's going to be either plus or minus sine of x or plus or minus cosine of x. And then the absolute value of that means you're basically just either dealing with sine of x or cosine of x. And in either case, those guys are less than or equal to 1, right? So you can say that this maxed thing in the formula, this r sub n of x thing, we could replace that with a 1. Okay, so note then that r sub n of x, because it's an absolute value, you could say it's going to be greater than or equal to 0, but it's going to be bounded above by this max thing. So the max of the n plus first derivative on the real numbers is just 1. And then divided by n plus 1 factorial times the absolute value of x to the n plus 1. Okay. Then you're going to take, so what you want to do is show that the limit of r sub n is equal to 0. That will prove that the Maclaurin series is equal to the function. Okay. So what you do is kind of a squeeze theorem. You take the limit as n goes to infinity of 0. So the limit as n goes to infinity of 0, of course, is 0. And then you consider then the limit as n goes to infinity of the absolute value of x to the n plus 1 all over n plus 1 factorial. And of course, this goes to 0, and the book makes a comment. It's because we noted in 9.1 that the limit of k to the n over n factorial goes to 0. It's kind of the same deal. There's alternate proofs to that fact. If you want to see one, just let me know. But those two sides will go to 0. Thus, the limit of the absolute value of r sub n of x will go to 0. And if you remember, we have this absolute value theorem, which says if the limit of the absolute value of the terms go to 0, then the actual thing goes to 0. Thus, and that was a 9.1 theorem. Okay, so thus the limit of r sub n of x goes to 0. Thus, you can say that the function and its Maclaurin series are equivalent. Okay, so thus the Maclaurin series converges to sine of x for all x. Okay. In practice, we're not going to play around with having to do that every time, because clearly that process was a bit annoying. So what you're going to have then is a kind of a chart of series that ideally you would have these memorized, but we don't have enough time to get that involved. And in this chart, they give you all of the intervals for convergence. that you would possibly need. Okay, so you can kind of cheat a little bit and just look at those from this point on. Okay, so anyways, yeah, that's great. We'll be able to then sort of leech on to whatever power series we build to create new series just via substitutions. We kind of saw that when we were dealing with the geometric series. So example 2, they want you to find the power series representation for sine of, oh, this is example 3 sorry. So example 3, they want you to find the power series representation for sine of x squared. Now you could go through and get the derivatives, and they kind of show the book doing that. But once you get to the second derivative, you're in a world of hurt. Right? So the normal process for producing these Maclaurin series is to get all the derivatives, evaluate the derivatives, put them into the formula, find the summation notation. It's just a nightmare, right? But what they're saying now is, now that we have this formula for the power series representation of sine of x, so let's say g of x equals sine of x, and that representation is the series -1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial from n equals 0 to infinity. What they're saying now is, in order to get f of x, all you need to do is plug x squared into this thing. Okay, so you'd have sine of x squared equaling the series -1 to the n times x squared to the 2n plus 1 all over 2n plus 1 factorial from n equals 0 to infinity. And then crud, I don't know what the heck I wrote there, but it's not right. You have the series, printing it up a little bit. You would have x to the 4n plus 2 all over 2n plus 1 factorial, and that turns out to be the representation for sine of x squared. Okay. You could do the ratio test and determine the interval of convergence. I don't think they asked for that in this example, though. Okay. So you could just clearly do an substitution. Then at 0 it would be x squared all over 1. At 1 it would be minus x to the 6 all over 3 factorial. And then at 2, x to the 10 all over 5 factorial, and so on. Okay, so you quickly produce the Maclaurin series representation via substitution. Okay, something we haven't played around with up until this point is the binomial series. You may have seen the binomial series with regards to Pascal's triangle, where you're quickly expanding things like 1 plus x cubed, right? So you can do that quickly via Pascal's, where the numbers in Pascal's triangle kind of tell you the coefficients on the polynomial that's generated by this. So cubing this, you could, literally sit there and FOIL it out, but the truth is it will just be 1 plus 3 somethings plus 3 somethings plus 1 somethings, right? And putting in some variables will be x cubed plus 3x squared plus 3x plus 1. So you can get around having to expand these things. You can go one more. So 1 plus x to the 4th would be x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1, right? Okay, so great, good stuff, huh? We're going to show you how to do that in general, so we'll be able to get power series representations for things like the square root of 1 plus x, which would be kind of important, especially if you're kind of looking to integrate something like this, 1 plus x squared, right? Because you could figure that out via substitution. We know how to do that now with trig subs, but anyways, we'll be able to get a power series for 1 plus x by rewriting it as 1 plus x to the 1/2, and then our binomial series will be a way of expanding upon these kind of Pascal triangle type expansions. Okay, and we'll, instead of having exponent restricted to a natural number, now we can look at real numbers for exponents. Okay, so they build that binomial series in example 4. So we have the binomial series. And so we look at, just in general, f of x equaling 1 plus x to the k. And then we're going to get a bunch of derivatives and kind of get a general formula for it. And we want it centered at 0. So anyways, f prime of x is going to be k times 1 plus x to the k minus 1. Let me give myself some room. Double prime. I just need enough to be able to kind of identify a pattern. Okay, I think that's good enough. And then the nth derivative. So you're starting at k, go k minus 1, k minus 2, all the way down to k minus this number with regards to the derivative. So it's just one less than the derivative. Okay, so it'll be minus whatever the derivative is minus 1. Okay, and then times 1 plus x to the k minus the number 3 is from the derivative, so n in this case. Okay, and then we evaluate all these at 0. Again, look for kind of a pattern, so it'd just be 1. This is k times k minus 1. K times k minus 1 times k minus 2, blah, blah, blah. So the nth derivative evaluated at 0 looks like it's going to be k times k minus 1 times k minus 2, dot, 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 all the way to k minus n minus 1. You distribute the negative and you get k minus n plus 1. So our power series representation for the binomial series is going to be 1 plus kx plus k times k minus 1 x squared over 2 plus k times k minus 1 times k minus 2 times x cubed over 3 factorial plus dot 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 plus k times k minus 1 times k minus 2 blah 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 down to k minus n plus 1 times x to the n all over n factorial, and then dot dot dot. Can we write that in summation notation? That will be the sum from n equals probably 0 to infinity of k times k minus 1 times k minus, probably 1 to infinity rather, k minus 2 dot 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 k minus n plus 1 times x to the n over n factorial. Yeah, 0 to infinity, I believe. Okay, so good stuff. They don't put it in summation notation. You could do the ratio test on this guy. I'm not going to go through that rigmarole, but the interval of convergence will be -1 to 1. Okay, and then they expand from there and kind of look at these funny versions of the binomial. So example 5, we have f of x equaling the 5th root. I think that says 5th root. No, it says 3rd root. Okay, so whatever. The 3rd root of 1 plus x. So this is basically just 1 plus x to the 1/3, right? So you'll be able to just replace k with 1/3, and you'll have your Taylor series. So here f of x would be 1 plus 1/3 plus 1/3 times 1/3 minus 3/3 minus 2/3 x squared over 2 plus 1/3 times -2/3 times I guess negative 1/3 minus what is it? 1/3 minus 6/3 is -5/3 times x cubed over 3 factorial plus on and on and on. So just doing a bit of a substitution. I don't know how far they want you to go with that idea. Yeah, so they just have you list the first couple terms, I think. Yeah, there it is. Okay. Right. And then they look a little graphing and show you how it's kind of converging around the center. Good stuff. Okay, from that point they introduce the kind of all of the power series representations into a nice chart. And then you can use that basic list to basically derive the power series for weirdly composited functions like cosine of square root of x. You can get products of functions like e to the x arc tan x just by multiplying out the entire thing. You can do division, so long division if you want the power series for sine of x over cosine x, which is tan x. You can square these things out. You can use like trig identities to pull this off. So if you know the power series for cosine, you could get cosine 2x via substitution and then form the power series for sine squared. And then finally you can use these things to get approximations for non-elementary integrals, okay, which will be kind of the last thing I believe we do, in this section. Okay, so let's maybe look at a couple in the homework here. These are just basic ones where you're building the expression. Number 7 looks like a division type problem. So we have f of x equals 10 tan x, and we want to get it, well, not really. So you could do this one by brute force. I'll do that. Just hold on, I want to kind of look ahead here what we're dealing with. Okay, so this one by brute force, f prime of x, let's start with f of x is 10 tan x. They just want the first 3 non-zero terms of the Taylor series. Okay, so f prime of x is going to be 10 secant squared of x. F double prime of x is going to be 20 secant x times the derivative of secant x, which is secant x tan x. Okay, so we have 20 secant squared x tan x. I need to evaluate all these characters at 3 pi. So we got 3 pi, tan of 3 pi. It's just freaking 0, isn't it? Darn it. Tan is sine over cosine, so I'm going to need another term, sadly. F triple prime of x, because this is going to be 0. And then f prime of 3 pi. So secant of 3 pi, so where is 3 pi? 1 pi, 2 pi, 3 pi. That's negative 1. Negative 1 squared is just 1, so times 10 is 10. Double prime of 3 pi. This is going to be so annoying because they're being jerks. So that's going to be 0. So I'm going to have to go way out. 40 secant x times the derivative of secant is secant x tan x times tan x. And then product rule, so plus, leave the secant squared alone now. 20 secant squared, the derivative of tan is secant squared x. So this will be 40 secant squared x tan squared x plus 20 secant to the 4th x. So the third derivative evaluated at 3 pi will be, looks like 20. 4 of 3 pi then. So the 4th derivative is going to be dealing with this guy first. We have 80 secant x times secant x tan x. So that will be secant x times tan squared x will be tan cubed x. plus the derivative of this part of it, right? So you get 80 secant squared x times 2 tan x times secant squared x. All of that will be 0 when you plug in 3 pi, but hopefully we'll get something from this part, right? So power rule, nope, we won't. 80 secant cubed x times the derivative of secant, which is secant x tan x, so that will be 0. So I have to go way to the fifth derivative, which you can kind of already see is a pain. So the derivative of this thing, it's really a secant squared part right there. So what do we have? Just taking, do any of these combine? And that would be a big no. So we have 160 secant x times tan x times tan cubed x. That will be a big 0 when I plug in 3 pi, plus taking the derivative of tan cubed. That will end up being a 0, whatever it is, because it's going to have factors of tan. Then plus this thing. So first taking the derivative of secant to the fourth, I'll get 320 secant cubed x times secant x tan x. Whatever that is, it'll just be a big 0. Then taking the derivative of the tan part, you'll have 80 secant cubed x times, there's a 2 in there, so this will be 160 secant cubed x times secant squared x. So that's going to give you secant to the fifth, which is negative. Is that true? But no, I'm taking the derivative of tan, so it's secant to the fourth. So that would be positive, and it's 160, way out at 160. Let's just, okay, and then this guy, you know, if you take the derivative of the secant part, you're going to get factors of tan, but then you're going to be able to take the derivative of tan, you're going to get another 80. Oh, what a freaking nightmare. Let's just go to Wolfram and see what they say is the fifth derivative, because I'm not trusting myself at this point. So DIFF of DIFF of DIFF of DIFF of DIFF of what was it, tan of x with respect to 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 x. Okie dokie. So it looks like that portion, when you plug in, you'll get 160 out of it. So is that the fifth derivative? 1, 2, 3, 4, 5. Yeah. Okay, so this will be, when you plug in 0, you're going to get, or when you plug in 3 pi rather, for the fifth derivative, yeah, you get, looks like you get 160. Or no, you're just going to get 16. Really? Why am I getting like 160 on my derivative? Oh, because there's a 10 in front of it. Okay, so we need to put a 10 in there. So this section just goes on and on. So yeah, it's you know, it's plugging in 3 pi. This first part here is going to give you 160 for that, and then the rest will be 0. So yeah, 160 for the fifth derivative. So the first 3 non-zero terms from this baloney, f of x would be 0 plus 10x plus 0x squared over 2 plus 20x cubed over 3 factorial plus 0 x to the 4th over 4 factorial plus 160 x to the 5th over 5 factorial. Okay. And that should be the answer. Let's see how many times I have to do this before I get it right. 10x plus 20x cubed all over 3 factorial plus 160 x to the 5th all over 5 factorial. Oh, and then you have to go minus the 3 pi, so that's going to be wrong. Okay, so this has to be x minus the 3 pi because it's, centered around 3 pi. So I have parentheses and parentheses, and it's trying to help me, but it's not being helpful. 3 pi, and then parentheses and parentheses minus 3 pi. And then hopefully that's right. Alright, that's great. Binomial on this guy, and they want it in summation notation because they are evil. Okay, so number 9. We have f of x equals the 4th root of 1 plus x, and well, they're not so evil. So we know our power series representation then will be 1 plus, because this is 1 plus x to the 1/4, 1 plus 1/4 x plus 1/4 times 1 minus 1/4, which is 3/4, times x squared all over 2 plus 1/4 times 3/4 times, okay, so this was n equals 0, I believe. This is n equals 1, n equals 2. Is that how it goes? Yeah, starts at 0. N equals 3. So 1/4, then 1 minus 1/4, then 2 minus 1/4 will be 5/4. 2 minus 1/4 is 5/4. So x cubed over 3 factorial, and then on, right? So using this formula, I think we could kind of guess at it, right? So it's 3 times 5 times 3 times 1, so 4n minus 5, and then it's like just n, x to the third power, so x to the n divided by n factorial. Okay, because they didn't give you the 4 though, so there's some 4's in here. So if you rewrote it, it would be 1 plus 1/4 x plus 3 times 1 all over 4 squared. And the way that their summation notation looks, they're writing it basically 3 times, or 1 times 3 rather. So they have 1 times 3 times 1 all over 4. So when n is 2, it's 4 squared. When n is 3, it's 4 cubed. Okay, times x to the second power all over 2. So I need that 4 to the n. So the next term would be 1 times 3 times 5 times 1 all over 4 cubed times x cubed over 3 factorial, and on. So I lost my 4 to the n in the denominator. 4 to the n. Okay. Ruh-roh. Start at n equals 2. Right, that's what I did. X to the n over 4 to the n. Let me me pause the video. I think I lost a negative. So these terms right here, if you remember, what the heck are they? They're scrolling back up. K times K minus 1, right? So yeah, I think there's a negative floating about. So this one would have been, the first one would have been 1/4 K times K minus 1. So this is K. And then we have 1/4 times 1/4 minus 1. There it is. So this is actually 1/4 times negative 3/4. So this would be a negative. So you have this -1 issue. This one would be negative, and this one would be negative as well. So this term is positive. This term is negative. So the even terms, to make those positive, you're going to want, so let me erase these signs down here. So this one, this is negative, this is positive, right? So this is negative, this is positive. So I need this guy to be negative, and then I need this other guy, yeah, that one's positive. So there'll be a -1 to some power, and we want the even one to be negative, so you put n plus 1, and that'll do it. Okay, then you're working with tables of power series. So number 10, you have f of x equals e to the x to the 6 all over 6. And if you go to your table, we note that g of x, if that equals e to the x, the expansion is 1 plus x squared over 2 factorial plus etc. So to get our formula for this, and we could write this in summation notation. Is that what they ultimately want, a summation? Yeah. So in summation notation is x to the n all over n factorial from n equals 0 to infinity. So g of x to the 6 all over 6 is going to be x to the 6 all over 6 to the n all over n factorial. Rewriting that, make it a little more pretty. X to the 6n all over 6 to the n times n factorial from n equals 0 to infinity. So that's pretty easy. Summation x to the 6n divided by 6 to the n times n factorial. Okay, so you're just doing substitution on those. For something like number 13 and 14, though, you're going to have to do some multiplication. So let's take a look at that guy. Well, number 13 isn't so bad. So let's let g of x be the series for sine x. And of course, that's just a sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial. And then this other function, h of x equals x to the 6, right? So if you want to know what is this f of x, you just multiply these two together. So you would have x to the 6 times this guy, which would be x to the 6 times this guy. So let's move the x to the 6 inside the summation. Seems like a scary thing, but it's really just a distribution. You'll get x to the 2n plus 1 times x to the 6. Add the exponents, so 2n plus 1 plus 6 is 2n plus 7 all over 2n plus 1 factorial from n equals 0 to n. So that wasn't so hard. So you get -1 to the n times x to the 2n plus 7 all over 2n plus 1 factorial. But this one, this e to the x sine x, you're actually going to have to do some long multiplication like you did in arithmetic to get the first 5 terms, right? So we'll say g of x is e to the x, and then h of x is sine x. They only want the first 5 terms, so we're 4 terms actually. Find the first 4 non-zero terms by multiplying or dividing the series. You could use the table to do this. I know them though. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. We want the first 4 non-zero terms, so let's just leave it at that. Hopefully that's enough. This other guy, sine, has all odd exponents, so it'll be x plus x cubed all over 3 factorial. It's basically just e to the x, but with the 1 x squared with these guys missing. Okay, and then cosine is just these guys. The other guys are missing. Right, it's kind of a cool. From there, you can derive all kinds of other cool rules and complex variables, but we don't do that here. Anyways, x to the 5th over 5 factorial plus x to the 7th all over 7 factorial plus x to the 9th over 9 factorial. And then to multiply them, you kind of just do it like you would in, elementary math. You kind of distribute. So first multiplying the x by everything. So I'm multiplying this times all of these. Okay, and you get x plus x squared plus x cubed over 2 factorial plus etc. I need to make sure I get those 4 non-zero terms. Then I'm going to multiply everything by this guy. Okay, so I'll get, and I got to line up so they are lined up by their exponents. So the first one is x cubed over 3 factorial plus x to the 4th over 3 factorial plus x to the 5th all over 3 factorial times 2 factorial, and that should be enough terms. And then I want to multiply this by everything. So the first term is probably all I need, x to the 5th over 5 factorial plus dot dot dot. Oh, and I lost my negatives in there, right? That's what I get for thinking I can have everything memorized. Sine of x has alternating signs, so it's not quite just as easy as taking the alternating terms from e to the x. It's not quite that easy, right? It's minus, plus, minus, plus. So I need to go through and rewrite those. The second portion here, right? This will be minus, minus, minus. Then you add column-wise. You need the first 4 terms. So you'll have x plus x squared minus, get a common denominator, right? So I have to multiply top and bottom of this by 3. So I get 3x cubed over 3 factorial minus 1x cubed all over 3 factorial will be plus 2x cubed all over 3 factorial. And then these guys will cancel. And then the 4th term, I don't even want to do that. So the denominator here is 6. No, it's 6 times 2 is 12. The denominator here is 120, 5 factorial. The denominator here is 24, I believe. Okay, so does 24 go in the 120? 5 maybe? Yeah, 0, 2. So I need to multiply top and bottom of that by 5. So I'll end up with 5x to the 5th over 120. The second guy I need to multiply top and bottom by 10. So I get minus 10x to the 5th over 120. And then the last guy is just x to the 5th over 120. Okay. So what am I getting? Negative 5, so minus 4. Minus 4x to the 5th over 5 factorial. Okay. And that's the first 4 non-zero terms, and you would have to proceed accordingly to get more. Let's make sure it's right. Someday. and then, you know, you pray it's right. Yay. Alright, so then you get the plot of the thing. You could use a graphing calculator or Desmos or something to get it. Then we're into being able to do these really cool integrals. Okay, so doing integrals, approximating integrals. And normally we wouldn't be able to do these by hand, right? But we're going to be able to do it now. So let's look at number 16, I guess. Use power series to approximate the thing. In number 17, when you get that power series, basically it's going to be kind of like what we did to get x sine of x, or whatever it was back here in number 13. You could just divide the power series by x. For number 17, you see how it says sine of x over x? You just get the power series for sine of x and then divide that thing by x, so it'd be negative. So sine of x over x is going to be the power series negative 1 to the n times x to the 2n all over 2n plus 1 factorial. Okay, and then do the integral of it. So I'll show you how that works. Okay, so I have the integral from 0 to 1 of e to the negative x cubed dx. Okay, so first you want to get a power series representation for e to the negative x cubed, right? So you have e to the negative x cubed. What you're just going to do is substitute it into the power series representation for e to the x, which we all know and love. 1 plus x squared over 2 plus x cubed over 3 factorial plus da da da, which of course equals a sum from n equals 0 to infinity of x to the n over n factorial. Okay, so plugging in negative x cubed, you get 1 minus x cubed plus x to the 6 all over 2 minus x to the 9th over 3 factorial plus blah blah blah. That's equal to the series n equals 0 to infinity of x to the well, there's a negative in there as well. I mean, it would be negative x cubed to the n, but then we're going to rewrite it, right? So it's a series n equals 0 to infinity. Does the 0 work in the expansion? 1, yeah, it seems to work. So you get negative 1 to the n times x to the 3n all over n factorial. Okay, so I could replace this thing with that. All right. So I'm integrating basically this 1 minus x cubed plus x to the 6 over 2. I need to get a good approximation, so they want the approximation to be error less than 0.0001. And it's pretty easy to make sure. You just kind of do an alternating series thing on it. Anyways, what do I have here? X to the 6. I need enough terms so I could see the pattern. X to the 9th over 3 factorial plus x to the, I guess it's 3 times 4. That would be 12 all over 4 factorial minus dot dot dot. So integrate term by term. That will give you x minus x to the 4th over 4 plus x to the 7th all over 7 times 2 minus x to the 10th all over 10 times 3 factorial plus x to the 13th over 13 times 4 factorial minus x to the, I guess it'll be 16th all over 16 times 5 factorial plus dot dot dot. And I need to evaluate this from 0 to 1. If you want to get the summation notation for it, it's again, you just kind of take the integral of this thing here. So you're going to end up with the integral being the series from n equals 0. Well, I don't know about the 0, but it'll be negative 1 to the n times x to the 3n plus 1 all over 3n plus 1 times n factorial. Let's see where we start. I think at 0 would work. 0, yeah. So you have n equals 0 to infinity of -1 to the n times x to the 3n plus 1 all over 3n plus 1 times n factorial. So evaluating this critter from 0 to 1, if you plug 1 in there, you're just going to get the series n equals 0 to infinity of -1 to the n all over 3n plus 1 times n factorial. And then minus plugging 0 in there will just be 0, right? The whole polynomial will just be a big fat 0. So you have this expression as kind of your answer. You want to do an approximation, and this thing right here is an alternating series, and it's going to fulfill the alternating series test for convergence. The limit of the terms will be 0. The terms are decreasing. And then if you remember, the way that worked is the actual sum minus s sub n is less than or equal to the next term in line. Okay, so what the trick to kind of figuring out a good approximation is just to expand this sum. So 1 minus 1 over 4 plus 1 all over 7 times 2 minus 1 all over 10 times 3 factorial plus 1 all over 13 times 4 factorial minus 1 all over 16 times 5 factorial plus 1 all over 19 times 6 factorial minus 1 all over 22 times 7 factorial, etc. And then you kind of just start looking at these terms, right? And you want to find, once you find that it's less than the error, your answer is everything that comes before it. And it's just the alternating series estimation theorem. Okay, so take these terms and put them in your calculator, and we're looking for something less than our error, which was, of course, now I scrolled over too far, 0.3 zeros and a 1, right? Okay, so I'll start out. You might want to start at 1/4, but that's 0.25, so that's not going to work. I'm going to start out at there. If I need to, I can go in the other direction. So divided by, let's use Wolfram, 1 all over 13 times 4 factorial. Okay, I need a decimal, please. It's nice that they give you the fraction, but I need the decimal. That's not good enough. 0.003. Okay, so the next guy then, (16 times 5 factorial) 0.0005. Still not good enough. So I go here. And I'm getting 0.1234. That does it. So your answer is everything before that. You consider that term that we just looked at as a sub n plus 1, and we just need the sum s sub n. Okay, so I need all the terms up to a sub n, which is this last term here. So our answer is this. Okay, and that gives you a pretty good approximation of the integral, believe it or not, with error less than what we just saw. So anyways, let's fill in the blanks here. It's approximately equal to, well, I need how many terms? 1. I start at 0, right? So 0. So this is 0, 1, 2, 3, 4, 5. So 0 to 5 of -1 to the n all over 3n. Where did it go? Oh, I'm putting it into the wrong. Okay, so 0 to 5 of -1 to the n all over, I believe it was 3n plus 1 times n factorial. And then apparently we need to get an approximation. Let's see if that's right first. They're not even going to let me guess. Okay, so far so good. Then I need to figure out what the heck this thing is. 4 decimal rounding. Okay, so let's move. Of course, I'm not going to be able to see it. Okay, so let's type it in here. Just 1 over 4 plus 1 divided by 14 minus 1 divided by 10 times 3 factorial, excuse me, plus 1 divided by 1 divided by 13 times 4 factorial, minus 1 divided by 16 times 5 factorial, and hopefully that's right. Yeah, so I got some weird parentheses. Okay, so I'm going to go and fix that. I don't even know why I have parentheses on that one. So originally I thought I would have to type it in as a product. I have an extra parentheses here. Okay, so there we go. They want 4 decimals, so they don't want an exact answer, but there is the exact answer if you needed it. So 0.8074. Okay, so that really is the climax of the chapter. Being able to do these integrals that you couldn't do previously. Okay. I mean, you could always kind of do a trapezoid or, Simpson's rule on it, I guess. But anyways, now you have another tool in your toolkit. Supposedly computers do this, but like I said, the Cordic method seems like I read somewhere that the Cordic method is the way to go. Anyways, thank you for watching. Thank you for tolerating me. Did I give you a video quiz? Man. Hold on. I don't think I did. Great. Okay, so we'll do the last problem in the homework. That'll be our video quiz. These are kind of hard anyways, so it probably wouldn't hurt you. I'm not going to kill you to do the last problem. Alright, so it's power series for this thing, sine of x all over x. I think it was from 0 to 1 dx. And our error, we want 0.3 zeros. So error less than 0.123. Let's not get too carried away with all the rewriting and expanding and rewriting. But anyways, first off, sine of x over x is just, I kind of wrote it above. You take the Maclaurin series for sine x and divide the terms of the series, the formula for the terms of the series by x. So you end up with negative 1 to the n times x to the 2n plus 1 minus 1, so just 2n, all over 2n plus 1 factorial from n equals 0 to infinity. If you must, you can expand it. I guess we might as well. So what are we getting for sine? Normally it would be like x, but you divide by x, so we get 1, and then minus x to the 2 all over 3 factorial plus, this would be over 5 factorial, but x to the 4th minus x to the 6 all over 7 factorial plus, and I need to keep going until I see a pattern. So the integral of this character is going to be x minus x cubed all over 3 times 3 factorial plus x to the 5th all over 5 times 5 factorial minus blah blah blah. So it's kind of clear what that is. We want to evaluate it, of course, from 0 to 1. So plugging 1 in there, we'll have 1 minus 1 all over 3 times 3 factorial plus 1 all over 5 times 5 factorial minus 1 over, we can suppose, 7 times 7 factorial. And then if you subtract away the thing evaluated at 0, you just get a big fat 0, right? So that will be our kind of answer. We want it in summation notation with the lower index starting at 0. So n equals 0 to infinity, and you can kind of tell it's going to be something like -1 to the n all over 2n plus 1 times 2n plus 1 factorial. Okay, so when n is 0, that will just be 1, but when n is 1, it'll be 3 times 3 factorial. When n is 2, it'll be 5 times 5 factorial. So I think that's going to be our answer for this first part. Oops, and I need to figure out how far I got to go, right? So, you know, you got to play that game where you need the value to be less than our error. So let's keep getting a couple extra. 9 times 9 factorial minus 1 over 10 times 10 factorial. Okay, and then kind of look at these guys, see how far off we are. So for that first dude, what do we need? So it's 1 all over 9 times 9 factorial. Let's see where we are. And that is way too good. So we get back up a little bit. Sorry, I found that very entertaining. Let's back up a little and just look at 1 over 5 times 5 factorial. We may not need too many terms to get a good approximation. Okay, so that guy is not going to be good enough. 0.0016. Right. We need, thank you, very little. We need, what did we need? 0.0001. So we need 0.0001. Okay, so let's look at 1 over 7 times 7 factorial. I believe that's going to do it. 7 times 7 factorial. Oops, it's not going to like that. Yeah, so that'll do it. That is something less than what we have. So this guy is like equal to 0.1234 times 3. So our answer is just going to be this. Okay, so you're going from n equals 0, 1, 2. So n equals 2 for the top. So our integral from 0 to 1 for our answer of sine of x all over x dx is going to be the sum from 0 to 1, 0 to 2, right? Because this is n equals 0, n equals 1, n equals 2, of -1 to the n all over 2n plus 1 times 2n plus 1 factorial. And then we need to get that, actually evaluate that thing. But let's make sure this is right first. So we have -1 to the n, too many parentheses, to the n, and now it's just, okay, I know. My cat is trying to perpetrate and make a mess. All over 2n plus 1 times 2n plus 1 factorial. Let's make sure that's all right. And then we can go to Wolfram to get our approximation. So far so good. So we need to plug that thing in there. I think we need 4 decimals. Yeah, 4 decimals. Okay, so 1 minus 1 divided by 3 times 3 factorial plus 1 divided by 5 times 5 factorial, and to 4 decimals. Our answer is going to be, so this is approximately equal to that, and this will be approximately equal to 0.9461. Okay. All right, so 0.9641, that'll do it for our quiz. That'll do it for chapter 9, supposing I have this correct. And I don't. Frick. What did I do? Looks right to me, buddy. I'm going to have to pause the video and figure out what I did wrong. I mean, everything is right. What's wrong? There's nothing wrong here. 0, 1, 2. It's the second term. Plug in 1, you get 3 times 3 factorial. Plug in 2, you get... Did I do the negatives wrong? So, all I could think of is this screwed up somehow. Okay, cat. Please do not... And now the cat is freaking out on top of all my other problems. Yeah, you are annoying me. Okay, let me pause the video and see what the heck's going on. I typed it in wrong. I switched the 4 and the 6. It's 946 when I put 9641. Okay, so that'll do it for me. That'll do it for chapter 9, and thank you for watching. And that was the video quiz, and I will see you next time.